Hi guys, glad you could be here today. We're talking about numbering systems, specifically binary. It's a very important concept to the computer scientist. To begin, let's kind of review about numbering systems in general. All numbering systems use unique characters, which we kind of think of as our numbers, to express a value. The base of the numbering system defines usually or always the number of unique digits in the numbering system and the base of each of our exponential columns. And you'll see what I mean. Another review, an exponent is expressed as a power. So if we write 10 superscript 3, we say 10 to the third power. 10 is our base number, 3 is our exponent. We calculate our exponential value by multiplying the base number by itself, exponent number of times. So in this example, 10 to the third power is the same as 10 times 10 times 10, or 1,000. Basic review. Numbering systems use columns to express our numbers, our values. Each column has a place value. The place value of each column is determined by taking the base of the numbering system to a given power. The power of the rightmost column is 0, the power of the next column to the left is 1, the next is 2, etc. We're used to working with base 10, the decimal numbering system. Base 10 gives us 10 unique digits, and we use those digits to define a value. Our digits are 0 through 9. 0 counts. 10 is the base of our columns in our exponential value. This is how we get our ones column, our tens column, and our 100s column. The ones column is 10 to the 0 power. Now you see what I was talking about, I hope. Any number to the 0 power always equals 1, our ones column. The tens column is 10 to the first power. Any number to the first power always equals itself. So 10 to the power of 1 is 10. Our 100s column in base 10 or decimal is 10 to the power of 2 or 100. And then 10 to the power of 3 gives us our thousands column. And of course, as we keep going over, we would be 10 to the power of 4 would be our 10,000s, etc. So in base 10, we're used to using decimal. We don't even think about the conversion that we do when we look at a decimal number. If we took a decimal number, for example, 3,486, we automatically put a 3 in our 1,000s column, a 4 in our 100s column, an 8 in our 10s column, and a 6 in our 1s column. We don't even think about the fact that we're multiplying 3 by 1,000, 4 by 100, 8 by 10, and 6 by 1 to get that decimal number or value, 3,486. We just do it automatically. A couple of other things for us to think about. There are many ways to express numbers. We could express a long format of 3,486 as 3 times 10 to the third power, plus 4 times 10 to the second power, plus 8 times 10 to the first power, plus 6 times 10 to the 0 power, or 3 times 1,000 plus 4 times 100 plus 8 times 10 plus 6 times 1. Many ways to express the same value. With binary, we're working with base 2. We have 10 unique digits to define our values. Sorry, I mean 2. Did I say 10? Back up. 2 unique digits to define a value, 0 and 1. 2 is the base of each of our columns' exponential values. And the reason that binary works so well working with computers is because we can equate binary numbers to electrical signals. So for example, 0 can equate to an electrical off, and 1 equates to an electrical on. So we use binary through the basic hardware of the system, and it's very important to understand how it kind of works. Now, some binary terms. One binary digit is called a bit. The number 1011 is 4 bits. 8 bits are a byte. The number 10100101 is 1 byte. That would represent 1 character of data. 4 bits are a nibble. Sometimes we just need a smaller bit than a byte. Leading zeros are insignificant, so just like in the decimal numbering system, 0001, 1011 is the same as 11011. Now, in some situations with binary, you may be asked to include those leading zeros. It depends on the situation, but the numbers are the same. Now, when we're working with binary, our first column, our least significant digit, instead of 10 to the 0 power is 2 to the 0 power because the base of our numbering system is 2. Again, any number to the 0 power equals 1. The next column to the left is 2 to the first power, and again, any number to the first power equals itself, so our next column is equal to. Then 2 to the second power, or 4, is our next most significant digit, and the next column is 2 to the third power, 2 times 2 times 2, or 8. As we keep going, we'll look at how we can convert from binary to decimal. When we're converting from a binary number to a decimal number, the first thing we want to do is write down the powers of 2. If you've noticed, the powers of 2 in the decimal equivalent are a doubling, so it's pretty easy to write down the powers of 2. I always start with the least significant digit, 2 to the 0 power. Remember, that's 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. Keep working my way over. Usually when working with computer systems, we usually only convert 8 bits at a time, so 2 to the 7th power is a high enough number for us to go with our powers of 2. So just keep working your way over to the left, doubling that number as you write down the powers of 2. This gives us our columnar values that we're going to work with as we convert back and forth. So we have our binary value and our decimal equivalent. Alright, now we're going to convert the binary number 10111. The first thing we want to do is, beginning with our least significant digit, start lining our binary digits up under the appropriate column. So this 1 is going to go over here in our ones column. This next 1 would go right beside it in our twos column. And we're just going to keep going, lining things up. We have a 0 in our 8s column. And lastly, a 1 in our 16s column. Again, we don't need to fill in these other digits because we know the zeros are the same as nothing. Okay, so we've lined up our binary number under our powers of 2 columnar values so that we're ready to convert this number to its decimal equivalent. Now, in order to convert it, we just take each of these numbers where we have a 1 and take the decimal value of that column, 1 plus 2 plus 4 plus 16, and we add up all those bits. So everywhere I have a bit turned on, my 16s column, my 4s column, my 2s column, and my 1s column, so looking at the values of the bits that are turned on based on our binary number, we can say that the binary number 10111 is equivalent to a decimal number 23. Now we have another number to convert, binary 11010. I'm lining my bits up. Sorry for the mouse movement, but I want to show you. Notice how I'm lining them up, starting over here at the least significant digit, lining them up, going across until I run out of bits. And and that way I know where they all belong. Put my bits in place. Now I have 116 turned on. I have the 8-bit turned on. Gives me a value of 8. I have no 4s in this situation. I have the 2-bit turned on, giving me a value of 2, and I have no 1s. The 1-bit is turned off. So again, I'm going to add up the value of all of the bits that are turned on. 16 plus 8 plus 2 equals 26. Decimal 26 is equivalent to binary 11010. Another conversion. Convert 100,100. Beginning with your ones column, line the digits up under their appropriate column so that you can begin the conversion. Notice that the 32-bit is on, giving us 32. The 4-bit is on, giving us 4. So binary 100,100 equals 32 plus 4, or 36. This is a very easy conversion to do. Please get out your worksheet and do those conversions. Let me show you where that is. You should be able to download the worksheet from the attachment section. Your first column is performing binary conversions. Down at the bottom of the worksheet, there is a powers of 2 columnar layout for you to use. When you're ready, return to the video and let's convert some decimal numbers to binary. Again, to begin, write down the powers of 2. Start with 2 to the 0 power is 1, 2 to the power of 1 is 2, etc., so that you have all 8 bits written down to work with on your powers of 2. Remember, when you're converting, doing binary conversions, sometimes if you're taking certification tests especially, you need to be able to do these binary conversions by hand without the assistance of any sort of calculator. That's why I'm trying to show you how to do it in the most easiest to remember way so that you can think of how to do it when you're stressed out trying to take a certification test. Write down the powers of 2. Begin with the number that you want to convert. We want to convert the number 21, starting with your most significant digit, the 128, our leftmost column, working your way across towards your least significant digit. Find the highest value, columnar value, that fits into your number. So for example, does 128 go into 21? No, it doesn't. It's too big. So I have no 128s in 21. Does 64 go into 21? No, it doesn't. So I have no 64s. I could put a 0 in that column, but remember, leading zeros are insignificant. Do I have any 32s in 21? No, so I could put a 0. Do I have any 16s in 21? Yes, I do. So I am going to turn on the 16-bit. 16 is the leftmost columnar value, less than 21. Now I need to continue on my conversion. So I have allocated 16 of our 21. So I have 21 minus 16, or 5, remaining to convert. I have 5 remaining to convert from our original 21. No 8s go in 5, so I'm going to put a 0 in that column. There is a 4 in 5, so I can turn on my 4-bit. Now, out of the 5 I had, that accounts for 4 of those bits, or those numbers, so I only have 1 remaining to convert. So, no 2, but I do want to turn on my 1-bit. So, 21 in base 10 is equivalent to the number 10101 in base 2. Notice the notation. where I've subscripted. Now, in our last example, step 5 was not really a step. It was just a repeating of steps 2 through 4 until there were no remaining value. So I'm just going to keep repeating, finding the highest columnar value that will fit and turning on that bit. Okay, how about 14? Let's start with our leftmost columnar value and work our way to the right. What is the highest columnar value that will fit into 14? 8. So I'm going to turn on my 8-bit. Now when I turn on that 8-bit, that allocates out 8. So I have 6 remaining to convert. There is a 4 in 6, so I will turn on my 4-bit. 6 minus 4 equals 2 that are remaining to convert. There is a 2 in 2, so I will turn on my 2-bit, leaving me none to convert. Error in the PowerPoint. So I will turn off the 1-bit. 14 to the power of 10 equals 1110 to the power of 2. Let's convert the number 36. What's the leftmost columnar value less than 36? 32. So I'm going to turn on my 32-bit. 32 of our 36 have now been allocated, so that leaves me 4 left to account for or convert. No 16s or 8s in 4, so I'll turn on that 4-bit, leaving me none left to convert. So I'll turn off my remaining bits. So base 10, 36 equals base 2, 100, 100. I hope you're getting the hang of it. It's not very hard doing binary to decimal and decimal to binary conversions. Go ahead now and finish the next part of that worksheet. Before you do, I want you to think about the powers of 2. It's pretty important information. In the beginning, when computer scientists were developing computers and things were going to be based on binary, the powers of 2 became very important. We saw already those first few bits account for a lot of our characters, and I'll show you how that works out here in a second. Other things about the powers of 2, though, have to do with some limits that we see a lot when we're talking about hard drive size, space of things, and things like that. 2 to the 10th power equals 1024, and 1024 is 1 kilobyte. 1 kilobyte is about 1,000. So in some write-ups nowadays, you'll see a kilobyte actually allocated as 1,000, 1,000 to the power of 1, but internally in the computer it's actually 1024 because it's 10 bits worth of information. Now a megabyte is 2 to the 20th power, and a megabyte is about 1,000,000 bytes. It is 1024 kilobytes, and in our new modern decimal only nomenclature, it would be 1,000,000, 1,000 to the power of 2. Next, 2 to the power of 30 is a gigabyte, about 1,000,000,000. Notice it's 1,024 megabytes, so 1,000 to the 3rd power if we were looking at it just without any binary equivalent. Next, 2 to the 40th power is a terabyte. We have a petabyte, an exabyte, and a zettabyte. You can continue on. There are some very large numbers. See if hard drive sizes get up to that size in your lifetime. Powers of 2 are very important. Now, because we have binary values for numbers, that works out great. But sometimes when we're working with data, we need character data, not just numbers. Again, in the beginning, the ASCII code table was developed by the American National Standards Institute to convert binary data to non-numeric, or in some cases maybe even numeric digital data. The process of converting from data that we understand to binary code is encoding and then converting that back is decoding. So this process is continually going on within the computer. Some binary ASCII code values, you see the letter A has been assigned this coded value in binary. The lowercase letter a has been assigned this value. If you see, the ASCII code table is very important. When you are a beginning programmer, you'll have to understand the significance of different data types. This helps explain that. If you tell the system that a value is a string, the system knows to convert that internal binary code to alphabetic data. If you say that the data type of a variable or a memory location that you have retained is numeric, that tells the system to convert that binary data to some sort of numeric value. So you can see it's very important when you're programming how you determine your data types. Some things for you to do now that you know how to do binary conversions. Search on Google for the binary game or Cisco binary game. It's on Cisco's website. It's a Flash application. It's very fun. It's kind of like Tetris. You solve the binary problems before your screen gets full. You can also investigate octal and hexadecimal numbering systems and use the calculator to check yourself. Set the view on your calculator to programmer mode and notice the radio buttons for your different numbering systems, binary, decimal, octal, and hexadecimal, and have some fun with it. I hope you really totally understand now how to convert between binary and decimal, and if you have any questions, let me know. Thank you.